Hello everybody, this is the second day of our crash course, and we're going to learn deep learning architectures and some important concepts of NLP and LLM. Deep learning architectures are the backbone of any neural network model, determining how the network processes data and learns patterns. The architecture defines the organization of layers, connections, and operations performed on the input data. The choice of architecture is critical because it directly impacts the model's performance, scalability, and computational efficiency. For example, convolutional neural networks, CNNs, are optimized for image data, while recurrent neural networks, RNNs, excel at sequential tasks like text and time series. With the rise of transformer models, architectures have become increasingly specialized, addressing challenges in processing diverse data types, handling large datasets, and integrating multimodal inputs like text and images. The Feedforward neural network, FNN, is the simplest deep learning architecture where information flows in one direction, from the input layer, through one or more hidden layers, to the output layer. Each layer consists of neurons, and every neuron in one layer is connected to every neuron in the next layer, forming fully connected layers. The network processes the input data through a series of matrix multiplications and applies activation functions at each layer to introduce nonlinearity. This enables FNNs to model complex relationships in the data. However, since FNNs lack mechanisms for retaining temporal or spatial information, they are not ideal for tasks requiring sequential context or spatial hierarchies. Instead, FNNs are commonly used for basic regression and classification tasks, such as predicting numerical outputs or categorizing data into discrete classes. While effective for small-scale problems, FNNs face limitations like high computational cost due to their dense connectivity and inability to scale efficiently. Convolutional neural networks, CNNs, are specifically designed to handle spatial data, making them the preferred architecture for image and video processing. The key component of a CNN is the convolutional layer, where small filters, kernels, slide across the input data to detect local patterns, such as edges or textures. Unlike fully connected layers, convolutional layers significantly reduce the number of parameters by focusing on local regions rather than connecting all neurons. Pooling layers, such as max pooling, are used to downsample the spatial dimensions of the data, retaining only the most critical features while reducing computational complexity. CNNs often include multiple convolutional and pooling layers, allowing them to learn increasingly abstract representations of the data. For example, in image classification tasks, initial layers might detect edges, while deeper layers recognize shapes, objects, or faces. Advanced CNN architectures like ResNet and EfficientNet improve performance by adding innovations like residual connections and optimized scaling. Recurrent neural networks, RNNs, are designed for sequential data such as time series, text, and audio. Unlike feed-forward networks, RNNs include hidden states that store information about previous inputs, enabling the network to retain memory across time steps. This makes RNNs well-suited for tasks like language modeling, where the meaning of a word often depends on the context provided by preceding words. Mathematically, at each time step, the RNN updates its hidden state using the input and the previous hidden state, applying a nonlinear activation function. Despite their effectiveness, RNNs struggle with the vanishing gradient problem, where gradients become too small to propagate through long sequences during backpropagation. This limitation reduces their ability to capture long-term dependencies, which has led to the development of improved architectures like LSTMs and GRUs. Long short-term memory networks, LSTMs, address the limitations of RNNs by introducing gating mechanisms that control the flow of information. These gates include: input gate determines which information from the current input should be added to the cell state. Forget gate decides what information to discard from the cell state. Output gate regulates what part of the cell state should be output at the current time step. These mechanisms enable LSTMs to retain relevant information over long sequences, effectively capturing long-term dependencies. For example, in a text generation task, an LSTM can maintain the context of earlier sentences while predicting the next word. The internal cell state acts as memory, storing information over extended sequences. While LSTMs are more computationally expensive than standard RNNs, they are widely used in applications like speech recognition, machine translation, and time series forecasting. Gated recurrent units, GRUs are a streamlined alternative to LSTMs designed to reduce computational complexity while retaining their ability to model long-term dependencies. GRUs simplify the architecture by combining the forget and input gates of LSTMs into a single update gate, which determines how much of the past information to retain and how much of the current input to incorporate. GRUs also use a reset gate to decide the extent to which the previous hidden state influences the current computation. These simplifications make GRUs faster to train and less prone to overfitting, especially for smaller datasets. Despite their simplicity, GRUs often perform comparably to LSTMs in tasks like language modeling and time series prediction, making them a popular choice in many deep learning applications. Autoencoders are a type of neural network designed for unsupervised learning tasks, where the goal is to encode input data into a compressed representation and then reconstruct the original input. The architecture consists of two main components. Encoder reduces the input to a lower dimensional latent space representation. Decoder reconstructs the input from the latent space. By learning to minimize the reconstruction error, autoencoders can capture the most important features in the data, making them useful for dimensionality reduction, similar to PCA. Autoencoders are also widely used for anomaly detection, where anomalies result in higher reconstruction errors compared to normal data. Variants like variational autoencoders, VEs, extend the basic architecture by incorporating probabilistic modeling, enabling the generation of new data samples from the latent space. Variational autoencoders, VEs, are a probabilistic extension of traditional autoencoders, designed to both compress input data and generate new samples from the latent space. Instead of encoding input into a deterministic latent representation, VEs encode the input into a latent distribution characterized by mean and variance. During training, the latent representation is sampled from this distribution, introducing a probabilistic aspect to the model. The decoder then reconstructs the data from the sampled latent variables. The loss function in VEs has two components. Reconstruction loss measures how well the reconstructed data matches the input. KL divergence regularizes the latent distribution to be close to a prior distribution, typically a standard normal distribution. This probabilistic modeling allows VEs to generate new data samples by sampling from the learned latent space. For example, in image generation, VEs can produce new images resembling the training data, but with novel variations. VEs are particularly useful in applications like data synthesis, anomaly detection, and semi-supervised learning. Generative adversarial networks, GNs, are a powerful architecture for generating high-quality synthetic data, including images, audio, and text. A GN consists of two competing neural networks. Generator attempts to create realistic data samples starting from random noise. Discriminator evaluates whether a given sample is real from the training data or fake, generated. The two networks are trained in a minimax game. The generator's goal is to create samples that fool the discriminator. The discriminator's goal is to distinguish between real and generated samples. Training GNs is challenging due to potential instabilities such as mode collapse, where the generator produces limited data variations. However, advanced GN variants like GANs, cycle GNs, and style GNs have significantly improved their robustness and applications. Transformers are deep learning architectures that rely on a self-attention mechanism to process sequences of data, replacing traditional recurrent mechanisms like RNNs and LSTMs. The self-attention mechanism allows transformers to weigh the importance of different input tokens relative to each other, enabling them to capture both local and global dependencies efficiently. Transformers leverage a fully parallelized architecture, enabling faster training on GPUs. Unlike RNNs, they process entire sequences simultaneously, making them more scalable for large datasets. Positional encodings are added to the input embeddings to retain sequence order. Transformers are the foundation of state-of-the-art models like BERT, bidirectional encoding for NLP, GPT, causal language modeling for text generation, and VIT, vision transformer for image classification. These architectures have transformed fields like NLP, computer vision, and multimodal AI. The encoder-decoder architecture is a general framework for sequence-to-sequence tasks, such as machine translation, text summarization, and speech recognition. The encoder processes the input sequence to produce a latent representation that captures the essential information. The decoder then takes this representation and generates the target sequence. In the context of transformers, the encoder uses self-attention layers to process the input, while the decoder combines self-attention with cross-attention, which focuses on the encoder's output. For example, in machine translation, the encoder processes the source language sentence, and the decoder generates the translated sentence in the target language, one token at a time. Key components include attention mechanisms, help focus on relevant parts of the input. Shared latent space enables transfer of meaningful information. This modularity allows the encoder-decoder structure to be adapted to various tasks, with transformers like T5 and BART further enhancing performance through pre-training and fine-tuning. Attention mechanisms are one of the most transformative innovations in deep learning architectures. Unlike traditional RNNs, which process data sequentially, attention allows models to selectively focus on specific parts of the input, making it possible to capture long-range dependencies efficiently. There are two primary types of attention. Self-attention computes relationships within a sequence, e.g., words in a sentence. It's the backbone of transformer models. Cross-attention computes relationships between two sequences, such as aligning source and target languages in machine translation. The self-attention mechanism processes input using query, key, and value matrices, enabling the model to weigh the importance of each token relative to others in the sequence. This eliminates the need for fixed-length memory states in RNNs and LSTMs. Attention has been particularly impactful in NLP, allowing transformers to outperform previous architectures and tasks like language modeling, question answering, and summarization. Additionally, attention mechanisms are now being applied to vision tasks, enhancing image recognition and segmentation models. Graph neural networks, GNNs, are a specialized architecture designed to process data structured as graphs, where entities, nodes, are connected by relationships, edges. Unlike traditional neural networks, which operate on fixed grids, e.g., images or sequences, GNNs can handle irregular and non-Euclidean data. The key idea in GNNs is message passing, where each node aggregates information from its neighbors to update its state. GNNs are widely used in domains like social networks, analyzing user relationships and behaviors; chemistry, predicting molecular properties based on graph representations of molecules; recommendation systems, modeling user-item interactions as graphs to improve recommendations. Variants like graph convolutional networks, GCNs, and graph attention networks, GTs, further enhance GNN capabilities by incorporating convolutional and attention mechanisms. Multimodal architectures are designed to process and integrate data from multiple modalities, such as text, images, and audio. These architectures align embeddings from different modalities into a shared representation space, enabling seamless interaction between modalities. For example, in image captioning, a multimodal model might use a CNN to extract image features and a transformer to generate textual descriptions based on those features. Similarly, in video analysis, models combine temporal features from frames, processed by RNNs or transformers, with audio features to understand context. One prominent approach is cross-modal attention, where features from one modality, e.g., text, guide the focus on another modality, e.g., image regions. Multimodal models are the backbone of applications like chatbots, processing text and speech, recommendation systems, considering user preferences across modalities, and augmented reality systems. Advanced architectures like Clip and DALL-E showcase the power of aligning visual and textual information for generative and classification tasks. Reinforcement learning, RL, architectures are designed for decision-making tasks where an agent interacts with an environment to maximize cumulative rewards. The architecture typically includes policy networks, define the agent's behavior by mapping states to actions. Value networks, estimate the expected rewards from a given state or state-action pair. The objective is to optimize the policy using algorithms like Q-learning or actor-critic methods. In deep RL, policy and value networks are implemented as deep neural networks, enabling the agent to handle high-dimensional input spaces, such as visual data from cameras and robotics. Natural language processing, NLP, is a branch of artificial intelligence that focuses on enabling machines to understand, interpret, and respond to human language in a meaningful way. NLP bridges the gap between human communication and computer systems by processing textual and spoken language data. Unlike structured data, like numbers and spreadsheets, human language is complex, ambiguous, and often context-dependent, making NLP a challenging field. NLP encompasses tasks such as language understanding, where the goal is to extract meaning from text or speech, and language generation, where machines create coherent and contextually relevant language. Common real-world applications of NLP include chatbots, e.g., Siri, Alexa, language translation, Google Translate, and sentiment analysis, analyzing customer reviews. In this lecture, we'll cover key concepts, foundational techniques, and modern advancements in NLP, illustrating how machines are increasingly capable of interacting with humans naturally and effectively. NLP involves multiple layers of linguistic analysis, each focusing on a different aspect of language. Syntax deals with the grammatical arrangement of words to form sentences. For example, parsing a sentence involves identifying its parts of speech, e.g., nouns, verbs, and their relationships. Understanding syntax is critical for tasks like grammar correction and language modeling. Semantics focuses on extracting meaning from text. For instance, understanding that bank can refer to a financial institution or the side of a river requires semantic analysis. Pragmatics goes a step further by interpreting the context and intent behind language. For example, "Can you pass the salt?" is understood as a request, not a question about ability. Morphology involves analyzing the internal structure of words. For example, breaking unbelievable into undash, believe, and able helps machines understand its meaning. Together, these components form the foundation of NLP systems, enabling machines to process and respond to language in a nuanced and context-aware manner. Text preprocessing is a crucial step in NLP that transforms raw, unstructured text into a structured format suitable for analysis. One of the first steps is tokenization, where a piece of text is split into smaller units, such as words or sentences. For example, "I love NLP" would be tokenized into "I love NLP." Stop word removal involves eliminating common words like the and is, which often do not contribute meaningful information. This helps reduce the dimensionality of the text without losing significant context. Stemming and lemmatization are techniques for reducing words to their base forms. While stemming crudely removes word suffixes, e.g., running, run, lemmatization is more sophisticated, considering the word's part of speech to return a valid base form, e.g., better, good. Lowercasing ensures text standardization by converting all characters to lowercase, which prevents the model from treating apple and apple as different entities. Proper text preprocessing is essential for improving the quality of input data and optimizing the performance of downstream NLP tasks. The bag of words, BAO, model is one of the simplest techniques for representing text data numerically. In BAO, a text document is converted into a vector of word counts or frequencies. For instance, given two sentences, "I love NLP" and "NLP is amazing," the vocabulary would be "I love NLP is amazing," and each sentence would be represented as a vector indicating the presence or frequency of these words. BAO ignores word order and grammar, which means it doesn't capture the context or relationships between words. While this simplicity makes it computationally efficient, it also limits its ability to understand complex language structures. BAO vectors are often sparse because most documents only contain a small subset of the entire vocabulary. Despite its limitations, BAO is effective for basic tasks like spam detection or sentiment classification and serves as a stepping stone to more advanced text representations. TF-IDF improves upon the bag of words model by assigning weights to words based on their importance in a document relative to a collection of documents, corpus. The two components are term frequency. TF measures how often a word appears in a document. Inverse document frequency. IDF penalizes words that appear frequently across many documents as they are less informative. By emphasizing rare but meaningful words, e.g., quantum, in a physics document, and reducing the impact of common words, e.g., the TF-IDF enhances text representation for tasks like document retrieval and topic modeling. It remains a widely used technique despite the advent of more sophisticated embeddings. Word embeddings revolutionized NLP by providing dense, low-dimensional representations of words, capturing their semantic meanings and relationships. Unlike sparse representations, e.g., BAO or TF-IDF, embeddings encode words in continuous vector spaces, allowing models to better understand similarities and differences between words. One of the defining features of word embeddings is their ability to capture semantic relationships. Popular models for learning embeddings include Word2Vec, trains embeddings using skipgram or CBOW, continuous bag of words. Techniques. GLOVE, Global Vectors, uses co-occurrence statistics to create embeddings. FastText extends word2vec by considering subword information, which improves representation for rare or out-of-vocabulary words. While traditional embeddings like word2vec provide static representations for words, contextual embeddings generate word vectors that depend on the surrounding text. For example, the word bank in riverbank will have a different embedding compared to financial bank, as its meaning depends on the context. Models like ELMO, embeddings from language models, introduce the concept of context-based embeddings by processing the input bidirectionally with recurrent networks. This idea was extended and refined in transformer-based models like BERT, bidirectional encoder representations from transformers. Unlike static embeddings, BERT generates unique word embeddings for each instance of a word in a sentence by leveraging its self-attention mechanism. GPT, Generative Pre-trained Transformer, on the other hand, focuses on unidirectional language modeling, generating embeddings as part of its predictive capabilities. Named Entity Recognition, NER, is a foundational task in NLP that involves identifying and classifying entities within text. Examples include recognizing names, John, dates, 2023, locations, New York, and organizations, Google. NER is essential for downstream applications like information extraction and question answering. NR models often use token classification, where each token in the input is labeled with an entity type, e.g., person, date, or marked as O outside any entity. Traditional NER systems relied on rule-based approaches or classical machine learning algorithms like CRFs, conditional random fields. However, modern NER systems use transformer-based architectures like BERT. By processing text in a bidirectional manner, BERT can understand the context of ambiguous tokens, leading to improved accuracy. NER is widely applied in chatbots, e.g., identifying user intent or location, legal document analysis, e.g., extracting case details, and healthcare, e.g., recognizing medical terms or patient information. Sentiment analysis is a widely used NLP task that determines the emotional tone or opinion expressed in text. Sentiment classification can be binary, positive versus negative, or multi-class, e.g., positive, neutral, negative. For example, analyzing a tweet like, "I love this product," would classify it as positive, while "terrible experience with customer service" would be negative. Early sentiment analysis relied on rule-based approaches, where predefined keywords and patterns indicated sentiment. However, these methods struggled with nuances like sarcasm, "oh great," "another delay," or context-dependent phrases. Machine learning models like naive Bayes and SVMs improved performance, but required substantial feature engineering. With deep learning, especially transformer-based models like BERT, sentiment analysis has become more accurate. These models capture context and nuances, enabling better detection of subtle emotions. Machine translation involves translating text or speech from one language to another, a challenging task due to differences in grammar, word order, and idiomatic expressions. Traditional approaches relied on rule-based systems or statistical machine translation, S&T, which required extensive language-specific data and often produced rigid translations. Deep learning revolutionized machine translation with sequence-to-sequence, seek-to-seek models. These architectures use an encoder-decoder structure, where the encoder processes the source language and the decoder generates the target language. The introduction of attention mechanisms, such as in Bodenow's attention, allowed the model to focus on relevant parts of the input sequence during decoding, significantly improving translation quality. Transformer models like BERT, T5, and GPT have further advanced machine translation by processing sequences in parallel and capturing long-range dependencies efficiently. Tools like Google Translate now leverage transformer-based models to provide high-quality, real-time translations for over 100 languages. Text summarization is the process of reducing a document to its essential points, saving time and effort while retaining critical information. There are two main approaches. Extractive summarization identifies and selects key sentences directly from the input text. This approach is simpler but may not create a coherent flow. Abstractive summarization generates new sentences based on the input, using natural language generation techniques. This approach requires deeper understanding and linguistic capabilities. Deep learning models, especially those based on transformers, have made abstractive summarization more practical. For example, BART and T5 are pre-trained models fine-tuned for summarization tasks, producing human-like summaries. Question answering, QA, is an NLP task where a model extracts or generates answers to user queries from a given text. QA systems are categorized into two types. Extractive QA directly identifies and extracts the answer from the input text. For example, given the question, who discovered gravity, and the passage, Isaac Newton discovered gravity in the 17th century, the model would extract Isaac Newton. Generative QA generates a complete answer using language generation models, even if the exact answer isn't explicitly mentioned in the text. Modern QA systems leverage pre-trained models like BERT for extractive tasks and GPT for generative tasks. These models are fine-tuned on QA datasets like SQuAD, Stanford Question Answering Dataset, to achieve high accuracy. QA has numerous applications, including chatbots, e.g., customer support, search engines, e.g., Google's featured snippets, and virtual assistants, e.g., Alexa and Siri. By combining retrieval and reasoning capabilities, QA systems significantly improve user interactions. Part of speech, PS. Tagging is the process of assigning grammatical labels, such as nouns, verbs, and adjectives, to each word in a sentence. For example, in the sentence, the cat sat on the mat, though would be tagged as a determiner, DT, cat as a noun, NN, and sat as a verb, VB. PS tagging is a foundational NLP task, enabling syntactic parsing, sentence structure analysis, and downstream applications like information extraction and question answering. Traditional POS tagging models include hidden Markov models, HMMs, which rely on the probabilistic relationships between words and tags, and conditional random fields, CRFs, which incorporate contextual dependencies for better accuracy. Modern NLP systems use transformer-based models like BERT for POS tagging. These models analyze the context of each word in the sentence, making them particularly effective for ambiguous cases. For instance, in I saw a bear, BERT can differentiate whether saw is a noun or a verb based on the surrounding context. Coreference resolution is a critical task in NLP that determines when two or more expressions in a text refer to the same entity. For example, in the text Alice went to the store. She bought some apples, the pronoun she refers to Alice. Early approaches to coreference resolution relied on rule-based systems and syntactic patterns. For instance, rules would dictate that pronouns often refer to the nearest noun of the correct gender and number. However, these methods were limited in handling complex or ambiguous cases. Modern models leverage attention mechanisms within transformer architectures like BERT. By analyzing the context of each word or phrase, these models can identify coreferent expressions more accurately. Language modeling is a fundamental task in NLP that involves predicting the probability of word sequences. It serves as the backbone for numerous applications like text generation, machine translation, autocomplete, and speech recognition. For instance, given the sentence, the cat is on the _____, a language model might predict not as the most probable word. There are two main approaches to language modeling. Causal language modeling predicts the next word based only on previous words. GPT, Generative Pre-trained Transformer, is an example of a causal language model. Masked language modeling predicts missing words within a sentence. BERT is trained using this approach, where random tokens in the input are replaced with a mask, and the model learns to reconstruct them. Pre-trained models like T5 combine both techniques for flexibility in multiple tasks. The effectiveness of modern language models stems from their ability to capture both local and global dependencies in text, enabling state-of-the-art performance in tasks such as dialogue generation and story completion. Word embeddings are an essential component of modern natural language processing, NLP, and machine learning models. They are used to map words or phrases from a vocabulary into vectors of real numbers, typically in a high-dimensional space. The reason embeddings are so important is because traditional representations like one-hot encoding are sparse and fail to capture the semantic relationships between words. Word embeddings, on the other hand, aim to represent words in a continuous vector space where semantically similar words are closer together. Popular methods for generating these embeddings include Word2Vec, glove, global vectors for word representation, and FastText. These methods allow machines to better understand language nuances and are foundational for a range of NLP tasks such as sentiment analysis and machine translation. Word2Vec revolutionized the way we think about word representation in NLP. It uses a shallow neural network to predict the surrounding context of a word, which in turn allows the model to generate a dense vector representation for each word in the vocabulary. The idea is that words that occur in similar contexts should have similar representations. Word2Vec offers two model architectures: continuous bag of words, CPOW, and skipgram. The CPOW model works by predicting the target word based on the context words, whereas skipgram takes a single word as input and predicts the surrounding context. For example, in the sentence, "The cat sat on the mat," CPOW would try to predict "sat" from the context words, "the cat on the mat," while skipgram would attempt to predict the context words based on Saturday. The key benefit of Word2Vec is its ability to learn meaningful word representations quickly, using a relatively simple architecture. Unlike earlier methods like latent semantic analysis, LSA, Word2Vec captures both the syntactic and semantic meanings of words, and it does so at a scale. One limitation, however, is that Word2Vec only considers words in isolation and ignores subword structures, which can make it less effective for morphologically rich languages or out-of-vocabulary words. The choice between the CPOW and skipgram models in Word2Vec depends on the specific use case and data characteristics. Let's first break down the key differences between them. CPOW works by predicting a target word from a set of context words. For example, given a window of surrounding words in a sentence, CPOW tries to predict the central word. The central idea here is that the meaning of a word is largely dependent on the words surrounding it. This approach is efficient for large datasets, as it requires fewer computations to learn from the context. On the other hand, the skipgram model works in the opposite direction. It takes a target word as input and tries to predict the surrounding context words. While this model is more expensive than CPOW, it has an advantage when dealing with rare words. The skipgram model performs better on rare and out-of-vocabulary words because it has the ability to model relationships in a nuanced way. Negative sampling is a crucial optimization introduced in Word2Vec to handle the inefficiency of training large vocabulary models using the full softmax function. In standard softmax, the model needs to compute the probability distribution over the entire vocabulary for every word prediction, which becomes computationally expensive as the vocabulary size grows. Negative sampling solves this issue by randomly selecting a small number of negative words which are not part of the context, and only training the model to predict these negative samples in addition to the true context word. Instead of computing the full softmax across all possible words in the vocabulary, the model only needs to compute probabilities for a small number of negative samples and the target word. This significantly reduces the time complexity of training from O-V to O-K, where V is the vocabulary size and K is the number of negative samples. GLOVE, or global vectors for word representation, is another popular method for learning word embeddings. Unlike Word2Vec, which focuses on local context, GLOVE is based on matrix factorization of the global word co-occurrence matrix. The co-occurrence matrix stores how often each word appears in the context of every other word in the corpus. The key idea behind GLOVE is that the relationship between words can be captured by the ratio of their co-occurrence probabilities. By factorizing this large co-occurrence matrix, GLOVE generates dense word vectors that encode both global and local word relationships. This approach captures more complex relationships between words that might not be apparent from local context alone. One advantage of GLOVE over Word2Vec is that it explicitly uses the global word co-occurrence statistics, which can provide richer semantic information. However, unlike Word2Vec, GLOVE does not rely on a predictive model, making it less flexible for certain tasks, but more efficient for capturing global word relationships. The global focus gives GLOVE an advantage in capturing relationships that are not obvious from local context alone. For example, GLOVE can better capture semantic similarities between words that might only occur together in specific contexts, such as financial and economic, or professor and academic. It uses these co-occurrence probabilities to generate word vectors that reflect these deeper relationships. On the other hand, Word2Vec, due to its local context approach, is often better for tasks where word prediction is required, such as in machine translation or speech recognition. In terms of training, Word2Vec can be more flexible and scalable, particularly when working with very large datasets. GLOVE, by contrast, is often preferred when dealing with a large corpus that requires capturing both local and global relationships efficiently. FastText, developed by Facebook, is an extension of the Word2Vec model that addresses one of the major limitations of Word2Vec, its inability to effectively handle out-of-vocabulary (OV) words. FastText improves on this by breaking words down into smaller units, character engrams, so that even words that weren't part of the original vocabulary can still be represented. This is especially beneficial for morphologically rich languages where word forms can change significantly. In these languages, words can have many different forms due to inflection and derivation. FastText captures these morphological properties by learning embeddings not just for words, but also for the character engrams that make them up. As a result, FastText is capable of generating high-quality representations for words that might otherwise be missed by models that treat words as atomic units. Word embeddings, as implemented in models like Word2Vec and GLOVE, traditionally treat words as atomic units. This can be problematic for languages with rich morphology, where the same root word can have many different inflected forms. For example, in English, the words run, running, runner, and ran all share a common root, but may be treated as separate, distinct words in the training data. FastText addresses this problem by breaking words into subword units, such as character engrams, allowing the model to capture morphological variations. This enables FastText to understand that running and run are closely related, as they share common subword units. The inclusion of subword information allows FastText to generate embeddings for words that are morphologically similar, even if they have not appeared in the training data before. Evaluating the quality of word embeddings is crucial to understanding how well a given model captures the relationships between words. There are two main types of evaluation: intrinsic and extrinsic. Intrinsic evaluation involves tasks that directly assess the quality of word embeddings themselves, while extrinsic evaluation involves measuring how well the embeddings perform in actual NLP applications. One common intrinsic evaluation is the word similarity task, where the model's word vectors are compared against human annotated similarity scores. For instance, the similarity between the words king and queen should be rated highly because they share semantic properties, and a good word embedding model should reflect this relationship in its vector space. Extrinsic evaluation, on the other hand, involves applying word embeddings to downstream NLP tasks and measuring how the embeddings impact the performance of these tasks. While intrinsic evaluation focuses on the internal quality of the embeddings, extrinsic evaluation is ultimately more important because it demonstrates how useful the embeddings are for solving real-world problems. Word embeddings live in high-dimensional spaces, typically ranging from 50 to 300 dimensions. While these high-dimensional spaces provide rich information about word relationships, visualizing them can be challenging. One common approach to make these embeddings more interpretable is dimensionality reduction, where the high-dimensional embeddings are projected onto a lower-dimensional space, usually 2D or 3D, for visualization. Two of the most popular techniques for dimensionality reduction are TSNE, T-distributed stochastic neighbor embedding, and PCA, principal component analysis. TSNE is particularly well-suited for visualizing word embeddings because it preserves local relationships between words. It maps similar words to nearby points in the lower dimensional space, making it ideal for visualizing clusters of semantically similar words. PCA, on the other hand, is a linear technique that focuses on capturing the global structure of the word vectors. While PCA is less effective than TSNE at preserving local relationships, it provides a more interpretable view of the embeddings. PCA works by identifying the principal components or directions of maximum variance in the data and projecting the embeddings onto these components. While word embeddings have brought a significant advancement in NLP, they have several limitations. One key limitation is their struggle with polysemy, which occurs when a word has multiple meanings depending on context. For instance, the word bank could refer to a financial institution or the side of a river. Word embeddings typically assign the same vector to all instances of the word bank, failing to capture these nuances. This issue is addressed in more advanced models like contextual embeddings, e.g., BERT, which take the surrounding context into account. Another limitation is that word embeddings do not capture long-range dependencies or the overall context beyond the immediate surrounding words. In models like Word2Vec, the relationship between words is encoded within a fixed vector, making it challenging to adjust the representation dynamically based on different usages of the word in various contexts. Additionally, word embeddings lack common sense reasoning. Although they can represent semantic similarity, they do not inherently understand the real-world implications of word relationships. For example, a model might understand that cat and dog are similar, but it won't automatically know that dog is an animal or that cats are generally more independent than dogs. While traditional word embeddings like Word2Vec and glove offer a fixed representation for each word, a more recent and powerful approach is the use of contextual embeddings. Contextual embeddings, as seen in models like BERT, bidirectional encoder representations from transformers, and GPT, generative pre-trained transformer, assign different representations to the same word depending on the context in which it appears. This dynamic representation allows the model to better capture the nuances of language and handle cases of polysemy more effectively. For example, in the sentence, "I went to the bank to fish," the word bank could be represented differently from the sentence, "I went to the bank to deposit money." In the first case, bank refers to the side of a river, while in the second, it refers to a financial institution. Contextual models like BERT capture these distinctions by encoding both the surrounding words and the broader context in which the word occurs, allowing them to generate more accurate word representations for different uses of the same word. This ability to account for context has led to significant improvements in NLP tasks such as named entity recognition, machine translation, and question answering. Models like BERT, which are pre-trained on vast amounts of text data and fine-tuned on specific tasks, have set new performance benchmarks across a wide variety of NLP benchmarks. Transfer learning has become an essential component of modern NLP. In the context of word embeddings, transfer learning involves using pre-trained word embeddings, like glove or Word2Vec, or pre-trained contextual models, like BERT, as a starting point for downstream tasks. This allows the model to leverage the knowledge learned from a large, general-purpose corpus of text and fine-tune it for specific tasks, such as sentiment analysis, named entity recognition, or text classification. By using transfer learning, we can save significant time and computational resources. Instead of training an embedding model from scratch, which can be computationally expensive and time-consuming, we can use pre-trained embeddings that already capture rich semantic information from a large corpus. These embeddings can then be fine-tuned on a smaller, task-specific dataset, where the model learns the specific nuances needed for the task at hand. For example, BERT can be pre-trained on a general corpus like Wikipedia and then fine-tuned for a specific task, improving performance on that task by leveraging general linguistic knowledge. Word embeddings are widely used in many NLP applications, and they are foundational to modern machine learning models that process text. One of the most common applications of word embeddings is in machine translation, where they are used to convert text from one language to another. Word embeddings allow machine translation models to capture semantic similarities between words in different languages, improving the quality of translations. In sentiment analysis, word embeddings help models determine the sentiment, positive, negative, or neutral, of a given text by representing words and their relationships more effectively. For instance, embeddings can be used to understand that happy and joyful are similar in meaning, so the sentiment analysis model can make more accurate predictions, even for new or rare words. Word embeddings also play a key role in improving search engines and recommendation systems. Search engines rely on a semantic similarity between words in user queries and indexed content, which is facilitated by word embeddings. For example, if a user searches for smartphone, the search engine can also return results for related terms like cell phone or mobile phone. In recommendation systems, embeddings help match products, articles, or content with user preferences by understanding the relationships between items. The development of large language models, LLMs, is built upon decades of innovations in natural language processing, NLP. In the early stages, rule-based systems were dominant. These systems relied on handcrafted linguistic rules, which were often rigid and non-scalable. They struggled with ambiguity and required extensive human effort to maintain. A significant shift occurred with the introduction of statistical methods, such as n-gram models and hidden Markov models, HMMs. These approaches used probabilities to determine the likelihood of word sequences, improving performance in applications like speech recognition and part-of-speech tagging. However, statistical models had limitations in handling long-range dependencies due to their reliance on Markov assumptions. Machine learning brought a paradigm shift where models learned patterns from data rather than being explicitly programmed. This transition enabled more flexible and scalable language understanding. The introduction of deep learning, particularly neural networks, further improved NLP models by allowing them to learn hierarchical representations. Finally, the introduction of transformers and self-attention mechanisms enabled large-scale training on massive datasets. These advancements collectively set the foundation for modern LLMs, making them capable of understanding and generating human-like text. Before machine learning became dominant in NLP, rule-based systems were widely used. These systems depended on linguists manually encoding grammatical rules and lexicons into structured formats. One of the foundational works in this area was Noam Chomsky's transformational grammar, which aimed to model human syntax using formal rules. Rule-based NLP systems were used in early applications such as machine translation, e.g., Systran, and basic chatbots, e.g., Eliza. While they performed well in constrained environments, they lacked flexibility. A major issue was scalability. Creating and maintaining rules for every possible linguistic scenario was infeasible. Additionally, these systems struggled with ambiguity. For example, the sentence, "time flies like an arrow," could have multiple interpretations that rule-based systems found difficult to resolve. As the complexity of language understanding grew, these systems became inadequate. This led researchers to explore statistical approaches where models learned patterns from data rather than relying on explicitly coded rules. Statistical methods revolutionized NLP by replacing deterministic rules with probabilistic approaches. Instead of explicitly defining linguistic structures, statistical models learned language patterns from large corpora. This shift improved scalability and adaptability. One of the earliest and most influential statistical models was the N-gram model. It estimated the probability of a word given the previous words, enabling more fluent text generation. However, N-gram models struggled with long-range dependencies due to their fixed window size. A more sophisticated approach was the hidden Markov model, HMM, which became a standard for tasks involving sequential data, such as part-of-speech tagging and speech recognition. HMMs modeled language as a sequence of hidden states with probabilistic transitions, significantly improving speech processing applications. Despite their advancements, statistical models had limitations. They often required large amounts of labeled data, and their reliance on Markovian assumptions limited their ability to capture complex dependencies. These constraints motivated the transition to machine learning-based models, particularly neural networks. The introduction of neural networks into NLP marked a significant shift away from traditional statistical approaches. Unlike N-gram models or hidden Markov models, HMMs, which relied on manually defined probabilities and feature engineering, neural networks allowed models to learn representations directly from raw text. Early neural network applications in NLP used multi-layer perceptrons, MLPs. These fully connected networks performed well on classification tasks, such as sentiment analysis and spam detection. However, MLPs had a major limitation. They treated input words as independent entities, ignoring sequential dependencies. To address this, recurrent neural networks, RNNs, were introduced. Unlike MLPs, RNNs process text sequentially, maintaining hidden states that carried information from previous words. This allowed RNNs to model dependencies over time, making them well-suited for applications like speech recognition and language modeling. Neural networks also enabled the shift from sparse, manually crafted features to dense word representations. Instead of representing words as one-hot vectors, neural models learned embeddings that captured semantic relationships between words. This advancement laid the groundwork for word embedding techniques like word2vec and glove, which further improved NLP performance. Recurrent neural networks, RNNs, were a major breakthrough in modeling sequential data, allowing NLP models to capture dependencies between words. Unlike feedforward networks, RNNs introduced recurrent connections, where the output from the previous step was fed back as input into the next step. This enabled models to maintain a hidden state that preserved context across time steps. The hidden state in an RNN acted as a form of memory, making it suitable for tasks like speech recognition, machine translation, and text generation. However, standard RNNs suffered from a key problem: vanishing gradients. When training deep RNNs, the gradients used for backpropagation became extremely small, making it difficult for the model to learn long-range dependencies. To address this issue, researchers developed long short-term memory, LSTM, networks. LSTMs introduce gates that controlled the flow of information, allowing the model to retain important information while discarding irrelevant details. A simplified variant, gated recurrent units, GRUs, was later introduced, reducing computational complexity while maintaining performance. Although LSTMs and GRUs improved upon standard RNNs, they still struggled with parallelization due to their sequential nature. This limitation ultimately led to the development of attention mechanisms, which improved efficiency and enabled more powerful architectures like transformers. Despite improvements with LSTMs and GRUs, sequential processing remained a major bottleneck in RNN-based models. They struggled with long-range dependencies, where important information from earlier parts of a sentence was diluted by later words. The attention mechanism, first introduced in neural machine translation, addressed this problem by allowing models to focus on the most relevant parts of the input sequence. Instead of encoding an entire input sentence into a single fixed-length vector, attention dynamically assigned weights to different input words, helping the model retain crucial information. In sequence-to-sequence models, attention improved performance by enabling the decoder to selectively attend to different words in the input sentence. This was particularly beneficial in language translation, where words at the beginning of a sentence might be important for generating words at the end. Moreover, attention mechanisms allowed for parallel computation, unlike RNNs, which required sequential updates. This efficiency boost paved the way for the development of the transformer architecture, which relies solely on self-attention to process text in parallel. The transformer model completely replaced RNNs in NLP models and became the foundation for LLMs. Seek-to-seek models were one of the earliest neural architectures specifically designed for NLP tasks requiring input and output sequences of different lengths, such as translation. The model consists of an encoder that compresses input into a fixed-length vector and a decoder that generates output from this compressed representation. However, the fixed-length vector was a bottleneck as it struggled with long sentences. If an important word was at the start of a long sentence, its impact might be lost by the time the decoder generated output. The solution was the attention mechanism, which allowed the decoder to dynamically focus on different parts of the input. This enhancement significantly improved translation quality and inspired later innovations, including the transformer model, which removes recurrence entirely and relies solely on attention for information flow. Self-attention is a critical innovation that enables models to compute relationships between words without relying on sequential recurrence. Instead of processing words one at a time, self-attention allows each word to attend to all other words in the sentence. The mechanism works by computing query, key, and value (Q-KV) vectors for each word, then calculating attention scores that determine how much focus each word should receive. This approach is far more efficient than RNNs because it allows parallel processing, leading to faster training and inference. This principle is at the core of the transformer architecture, which completely replaced RNN-based models. Transformers enable large-scale pre-training on vast datasets and form the basis for models like BERT and GPT. Since transformers process words in parallel rather than sequentially, they lack the natural ordering inherent in RNNs. To address this, positional encoding is added to input embeddings. Positional encodings are special vectors that represent word positions in a sequence. The most common method uses sinusoidal functions, where different frequency waveforms assign unique position values to each word. This ensures that word order information is incorporated while maintaining efficient computation. These encodings allow transformers to capture word order without requiring recurrence. Unlike RNNs, where position is inherently built into the sequential processing, transformers must explicitly encode this information to maintain meaningful word relationships. One major limitation of RNNs was their sequential nature. Each word had to be processed in order, which made training slow, especially on large datasets. Transformers eliminated this bottleneck by computing self-attention in parallel across all words. Parallelization significantly reduced training time, making it feasible to train massive models on billions of tokens. This efficiency enabled scaling to billions of parameters, leading to models like GPT-3 and BERT. Additionally, transformers use techniques like layer normalization and residual connections, which improve training stability. These optimizations have allowed NLP models to move beyond small-scale datasets to web-scale corpora, unlocking emergent capabilities in large models. Before pre-training, NLP models were trained from scratch for each task, requiring large labeled datasets. Pre-training plus fine-tuning solved this by first training models on massive corpora using unsupervised objectives, then fine-tuning on smaller, task-specific datasets. Pre-training methods include masked language modeling. MLM BERT-style models predict missing words in a sentence. Autoregressive modeling. GPT-style models predict the next word given previous context. These approaches enabled models to generalize better and perform well across multiple NLP tasks without requiring extensive labeled data. This paradigm shift paved the way for LLMs. The evolution of pre-trained models began with ELMO, embeddings from language models, which introduced contextual word embeddings, meaning the representation of a word changed depending on its context. BERT 2018 refined this by using bidirectional transformers, allowing it to understand both left and right context when encoding words. This was a major breakthrough for tasks like question answering and named entity recognition. Meanwhile, GPT 2018 took a different approach, using autoregressive training, where models generate text one word at a time. This enabled high-quality text generation, making it ideal for chatbots and creative writing. These innovations laid the groundwork for scaling models to billions of parameters, leading directly to LLMs. As models grew, researchers observed that performance scaled predictably with model size, dataset size, and compute power. This discovery, known as scaling laws, Kaplan et al. 2020, showed that larger models consistently achieved better results. Crucially, emergent abilities appeared in larger models, capabilities that were absent in smaller models but suddenly emerged at scale, such as few-shot learning. These findings justified the push toward billion-parameter models. Scaling laws guided the architecture of models like GPT-3, where increasing model size continued yielding improvements, as long as data and compute scaled proportionally. Previously, NLP models required task-specific fine-tuning. However, few-shot learning enabled models to learn new tasks from just a few examples without explicit retraining. Even more surprising was zero-shot learning, where LLMs perform tasks they were never trained on simply by understanding instructions. For example, GPT-3 could translate text without being explicitly trained for translation, demonstrating real-world generalization. This ability is one of the defining characteristics of large-scale pre-trained models and set the stage for the widespread adoption of LLMs. Thanks for watching. This concludes the day 2 of our course. Hope you enjoy it. For more tech courses and interview materials, please go to our website bowsy8.com.